All right, so let's look at chapter 3. So for number 44 here, we're solving an exponential equation. Now remember, when you're solving an exponential equation, you always want to make sure you get the base by itself. I'm going to change the color here. So we want to get this 16 to the n minus 7. We want to get that isolated. So I'm going to subtract 5 from both sides. So when I do that, we get 16 to the n minus 7 equals 19. Now remember, on your final, you're not going to be able to use a graphing calculator. So you want to make sure that you know how to solve this if you're going to be using a scientific calculator. And an easy way to do that would be to take the log of both sides. If I take the log of both sides, I'm going to do 2 steps in one. Or if I take the log of both sides, we can move that exponent that was here and put it in front of the logarithm. So I'm going to just do that in this step as well. And then equals, again, we're taking the log of both sides. We'd have the log of 19. So to solve this, I'm going to divide both sides by log of 16. So now I'd have n minus 7 on the left and log of 19 divided by log of 16 on the right. And actually, I could actually do that on my calculator. Log of 19 divided by log of 16 on your scientific calculator gives you a value of 1.062 approximately. And so now all I have to do to solve for n is add 7 to both sides, and I get 8.062. And that's how I do number 44. All right, let's look at 45. So 45 has 2 parts to it. So in the first part, part A, we're just going to simply figure out what log base 3 of 81 is. Remember, if I'm going to do that without using a graphing calculator, I want to make sure that I change the value, the value here to have a base that's going to match this base. We want these two bases to be the same, because then you'll see in a second, or remember the property that will allow us to be able to simply evaluate what the solution would be. So I got to figure out, well, what exponent would I apply to 3 to get 81? Well, 3 to the 4th power is 81. So whenever our base here for our logarithm is the same as our base that has the exponent, your answer is the exponent. So your answer would simply be 4 for part A there. For part B, what I'm going to do there is I'm going to change this to exponential form. Okay, so we're going to take and drag that base over. So I would end up with 8 equals x to the 3/2 power. Now, in order to solve this, you've got to remember our properties of exponents. We want to get rid of that exponent, so I'm going to multiply each side by the reciprocal, which would be 2/3. Because then by doing that, we'd end up with just x on the one side. So I'm going to put it on the left here. So it'll be x equals. And then to simplify what 8 to the 2/3 power would be, remember we can break that up into the root and then the power, meaning the third root of 8 would be 2. And then we'd have 2 squared, which would give us 4. So that would also give it, so both of those parts A and B would have a solution of 4. All right, let's look at number 46. So for 46, we're solving a logarithm equation. Now, just like when we solve a exponential equation, we're solving a logarithm equation. We want to make, well, there's a couple approaches we can take. In this case, what I want to do is I want to get the log by itself. Isolate the logarithm. So now we can't take 7 minus 4 because 4 is attached to that variable. Those are not like terms. So I'm going to start by subtracting 7 from both sides. When I do that, I get negative 4 log of x equals 3. I want to get that log by itself, so I'm going to divide both sides by negative 4 now. And I get log of x equals negative 3/4. So now to solve this, we're going to have to change the form it's in. Now remember, this is a common log, so my base is 10 here. So remember, we can take that base and drag it over, and the negative 3/4 would be your exponent. So in other words, writing this, converting this from logarithm form to exponential form, we get x equals 10 to the negative 3/4 power. And when it says give it an exact answer, that would be our solution. And then when it says to also find the give the decimal approximation to the nearest hundredths place, well, we could just type that in our calculator. 10 to the negative 3/4 power would be equivalent to 0.18 if we round to the nearest hundredths place. All right, for number 47, it says it's simplified down to one logarithm. So remember the different properties of logarithms. Remember this, time that we have a value in front of our logarithm, we can move that as an exponent. So that would be the same as log of y to the 1/2 power. And now we're going to combine all these as a single logarithm. So remember, if we're adding separate logarithms, we can combine it as a single logarithm using multiplication. If we're subtracting separate logarithms, we can combine it as a single logarithm using division. So here we have multiple things going on. So I'm going to have the log of this giant quantity, and we'll have x times y to the 1/2 power, and we divide by z. And that's all you'd have to do. That'd be your answer. That's a single logarithm. Let's look at number 48. Number 48, we're going to separate this out into separate logarithms, and even 4 logarithms, because we have 4 different variables there. So let's start by just breaking this all apart. So we have a log of x squared, and then since we have where we're multiplying by w to the 6th, so then it would be plus log of w to the 6th. And then we're dividing by both y and we're dividing by z cubed. So it would be minus log of y minus log of z cubed. And now let's take care of all those exponents. So those exponents are going to move in front of the logarithm. So this will be the same as 2 log of x plus 6 log of w minus log of y, because there's no exponent there. And then be minus 3 log of z. And those are our 4 separate logarithms. So we've met the criteria there for that. All right, number 49, solve logarithm equation. Now this one, if you notice, the previous logarithm equation that you did in number 46 just had a single log. Well, here we have multiple logarithms. So what we're going to do is we're going to combine these logarithms in one side, combine those as a single logarithm. So since we're adding, we're going to multiply those values. So when I write this as a single logarithm, it'd be the logarithm of x plus 2 times x equals, and then on the right side, I'm going to write that as log of 2 cubed. Or you could say log of 8. All right, so now both sides, we have the log is the same on both sides. So now we can say the values, because we're trying to solve for x, so we already have the logs being the same on both sides. So what we're trying to do is we're trying to figure out what values for x would make this also true on both sides. So we can just isolate those. So we would have x plus 2 times x, I'm just going to put the x over here, equals 2 cubed, which is 8. Or we can say x squared plus 2x equals 8. And now to solve this as a quadratic, so I'm going to get everything on one side, because then I can either use the quadratic formula or I could use factoring. I always want to start with factoring because that's going to be the easiest, and I'm going to look to see what two numbers multiply together to be negative 8 that add together to be a positive 2. Well, that would be a negative 2 and a positive 4. And now I can set each of those factors equal to 0 and solve. So our solutions would be 2 and negative 4. But with these, we always want to make sure that we look to see if there's any extraneous solutions. Because one of the rules with logarithms is you can't take the log of a negative value. So if I put 2 in here, if I put 2 in both of those values for x, we'd have 2 plus 2, which is 4. So we'd have the log of 4 plus the log of 2. Okay, there's nothing there that doesn't make it's not possible. But when we put negative 4 in here for x, we would have log of negative 4 plus 2, which would be the log of negative 2, and we'd also have a log of negative 4. So we cannot take the log of a negative number, so this would be an extraneous solution. So it's a solution that doesn't work, but x equals 2 would be a solution that does work. All right, let's look at number 50. So this one, we also have multiple logarithms. So we're going to approach this one very similar to what we did on the previous one, where we're going to write this as a single logarithm on the left side. So we would have the log of x minus 4 times x plus 5 equals 1. Now the problem is there's no log on the right side. And we can't just introduce a log on the right side without also introducing another log on the left. And we don't want to have multiple logarithms on the left side. So what we're going to do is we're going to put this in exponential form. So I'm going to take, remember the base here, for this log, it's a common logarithm, so base is 10. So I'm going to drag that over to the other side. So we'd have 10 to the first power. And on the left side, we'd have x minus 4 times x plus 5. On the right side, we'd have 10 to the first power, would just be 10. And now I can multiply those together. And you might say, well, why can't I just set each of these equal to 10? Well, the only time that we can set each of the factors equal to something is if the right side is equal to 0. So we can't do that yet, but that's going to be something we're going to get to. So if I multiply these together, we would get x squared plus 1x, or just x, minus 20 equals 10. And if I subtract 10 from both sides, we get x squared plus x minus 30 equals 0. Now what I'm going to do is now I'm going to try to factor this. So I'm going to be looking for two numbers that multiply together to be negative 30 that add together to be a positive 1. And that would be a positive 6 and a negative 5. And now that it's equal to 0, we can set each of those factors equal to 0 and solve them. But again, we want to check for extraneous solutions. And negative 6, if I plug that in, negative 6 minus 4 would be negative 10. And negative 6 plus 1 would be, or negative 6 plus 5 would be negative 1. In either case, we can't have the log of a negative number, so this one is extraneous. But x equals 5 would be an actual solution. All right, so for this one, we're going to look for the initial population of deer. So the initial population represents when no time has passed by. So t in this problem represents the time, and the p of t represents the total after a period of time. So what is the initial population of deer? It is not 99. Do not make that mistake. On a multiple choice test, chances are that's going to be, that if this were the question, that would be one of the choices. So please do not be deceived by that. You have to remember what an initial population represents. An initial population or initial value represents the total after no time has passed. So I'm going to put 0 in here for t. So when I do that, negative 0.4 times 0 is just 0, and anything to the 0 power is 1. So e to the 0 power would be 1, which is not going to have any impact here because 99 times 1 would be 99. So in essence, we have 1200 divided by 100, which gives you 12. So the initial population would be 12 deer. Now for part B, this one's going to involve a little bit more work. We want to figure out when will there be 1,000 deer. So now we're trying to figure out how long it's going to take for the total to be 1,000. So we need to solve this equation. So to solve the equation, we're going to multiply both sides by 1 plus 99e to the negative 0.4t. And when you do that, these would cancel out. And instead of rewriting all of this, well, I might as well go ahead. So we'd have 1 plus 99e to the negative 4t equals, whoops, times 1,000 equals 1,200. I'll mention in a second what I was going to actually skip to. All right, so we want to solve this for t. So one of my goals is I need to get the exponential piece by itself. So I'm going to divide both sides by 1,000. So if I divide both sides by 1,000, we would get 1.2 on the right. So we're just that much closer to getting this base, that exponential piece, by itself. Now what I was going to mention earlier is going back to what I had in red to what I had over here in green. We could have actually gotten directly, we could have connected these two steps without doing anything I did in purple. Because any time that we have a variable in the denominator, we can just take this piece and switch them. So if we did that, we'd have 1 plus 99e to the negative 0.4t power on the left side, which is what we have here, equals, and then we'd have 1200 divided by 1000, which is 1.2 on the right side. So like I said, we could have just skipped directly to that, but I want you to see why we could actually go through that process, or why we could actually use that shortcut. All right, so now I want to solve this for it. I want to get the base by itself. So I'm going to start by subtracting 1 from both sides. So I'd have 99e to the negative 0.4t equals 0.2, or just 0.2. And now I'm going to divide both sides by 99. When I do that, 0.2 divided by 99 would be 0.002 approximately. And so again, this is an exponential equation. So to solve this, we could either take the log of both sides or the natural log of both sides, but since we're dealing with a base that's e, Euler's number, it makes more sense to use the natural log. So I'm going to take the natural log of both sides. And remember, the natural log of e is just 1. So now I would have the natural log of 0.002 on the right. So to solve for t, I would divide by negative 4. When you do that, you get 15.5, or approximately 16 days. That's how long there would take to reach 1,000 deer. Oh, I'm sorry, 16 years. Sorry, time is in years in this one. All right, so this one, they just want us to graph and identify the asymptote and the y-intercept. I'm also going to identify the end behavior, because I think that would also be good to review for this one. So remember, if our b value is between 0 and 1, it represents exponential decay, and this represents our initial amount. So we would have a y-intercept at 100, and it would be decreasing from left to right with the horizontal asymptote at y equals 0. Okay, so y equals 0 would be our asymptote. The y-intercept would be at, where x is 0, y is 100. So those are the pieces that they asked for. But just to review, if we wanted to talk about the limits here. So this would be referring to the right side of the graph. The right side of the graph is approaching 0. And this would be referring to the left side of the graph. The left side of the graph is approaching infinity. So that would be number 52. And this last one, sketching a graph of y equals the opposite of log of x plus 4 minus 3. So we have a few things going on. So this means it's moving to the left 4. This means it's moving down 3. And then this means it's being flipped vertically. So remember, our parent function would look like this. Okay, so we would have a vertical asymptote at x equals 0. We'd have an x-intercept at 1, 0. But now we're going to flip that vertically, and then we're going to move it left 4 and down 3. So if I move it to the left 4 units, our vertical asymptote now would be at negative 4. And that point that was here at 1, 0, we're going to move that to the left 4 units and down 3 units. So it'd be kind of down here. We're at negative 3. And then we're going to flip it. Whoops, I don't know what happened there. There we go. And so our graph would look something like that. So that's what a graph of that logarithm function would look like for number 53. So that's it. So good luck as you finish reviewing chapter 3.